it actually scales towards the worst case. As you add more keys and values to this dictionary in this memory model, okay, it becomes less performant per key, right? It becomes less of a chance that we'll find the right one. It's more likely that the wrong key will be found, right? So in the key value pair model, your cache, your memory data, is being filled with all this giant expensive value data and then immediately being thrown away because it's not even being used because it's the wrong one we want. So here's a better idea. Now this is not a general case. Remember, I'm not suggesting I've reinvented the dictionary. There is no abstract solution. It doesn't exist. There's no good abstract solution, okay? So in the common case, when we're just searching for the key, right? What is it that we really want? We really just want two different portions of memory, right? We want the key all by themselves so that when we bring a key, we automatically know that we're probably going to throw it away because it's the wrong one. Say we're looking for 333, right? If we access 3333, only the keys get loaded, right? And 3333 might be associated with a very cheap array index, which is much less expensive to bring into memory. And so in this case, we bring it in, we find the key, and then we look for the value, right? We associate that key immediately with an index inside of the value array. So what have we done? We've separated the two memory accesses. We're going to look at a better example, more code example. But the idea is that you want to defer the worst case as long as possible. Where the worst case is that you won't find the value you're looking for. And in this case, this is a much better solution. Okay? So what are the conclusions from this? So you want to solve for the most common case in your code. The most common case in the dictionary, it was that you would not find the key, right? You wouldn't find it. That's the most common case. And you want to avoid solving the most generic case, which is often what we do in programming. We generally assume things like, oh, the generic case will solve everything. But more often than not, solving the generic case actually scales towards your worst case scenario. You want to solve the most common case. You want to understand the characteristics of how data flows through a system. And by that I mean, how does the data interact with memory? How is it brought in? What is brought in along with that memory? What else comes in with that memory? Does the code actually utilize that memory as I access it? And the rule of thumb in this is that where there's one object, there are many objects. Do not generalize your solutions. Generalizing your solutions is crap. It's low performance. So here's a question. I love this question. Can't the compiler optimize it? Right? No. Compiler is a tool, not a magic wand. We're going to see what the compiler can optimize for us. So let's just do a little review. This is very basic. Okay, just very quick review. This is not important. So we typically think of these operations as kind of expensive on our computer, right? So like square root can be anywhere between like 13 to 30 cycles, let's say max, right? On a CPU. And the transcendental functions such as sine through arctangent, whatever, they're fairly expensive, right? But if you think about it, the vast majority of our instructions are not this expensive, right? Like simple addition may take 1 to 2 cycles, right? Accessing a character or doing something on a character in a string, probably a 1-cycle operation, right? It's very cheap. These are very expensive, but they're very rare, right? But we typically think of these as the culprits of performance problems, right? Now let's take a look at the memory hierarchy. Accessing a piece of information in main memory costs 200 cycles. It costs just as much as doing the transcendental. And that's a way more common case. L2 cache is 20, L1 is like 3 cycles, yada, yada, yada. Right? So this is just to give you like just an idea before I jump into the code example. So main memory, 200 cycles, right? So let's take a look at a piece of code. So we have this piece of game code, right? It's pretty typical. You might see something. We have an entity, which may represent some kind of object in our game world, right? And it has like a position, a velocity, magnitude, maybe some properties like names of things, a model, and it has this function, right? It's called update magnitude, right? And what does this function do? It updates the magnitude of this entity, right? Just this entity, right? So it's very typical code, right? You might see something like this. And if someone were to look at this, you're an optimization engineer, you're like, oh, that square root is the problem, right? That's the expensive part, right? No, it's not even close. Let's take a look at the assembly. I know this is a little bit terse, but I want to look at this, right? So we look at the disassembly of this function in Visual Studio. What are we going to see? The first red arrow, we have a move from a pointer, so that's accessing memory. That's a read from the cache, and it's a miss. It's not in cache, so that's like 200 cycles. That's how much that costs. Then later on, we're like, oh, look here, we have another move SS from another place in memory. It's different, and I did some of the math here and found out it's way different. It's not even in the cache line, so that's another 200 cycles, just lost. The square root that we were worried about, that happens right around here, what does that equal? Oh yeah, right here. What does that equal? Oh, so that's 30 cycles, right? It's so expensive. Okay? The memory access outside of the previous cache line of this one, there's another one here. It's another 200 cycles, right? The real work that was done in this function is actually in the memory access. So now the question becomes, how does this function scale to multiple entities? Well, we're going to experience the same cache misses on every function call. Every function call will experience those cache misses because these entities are singular and they're in different locations in memory. And we spent time, working on the L2 cache versus the actual work being like additions and all the other stuff we're doing. The actual time we spent on the L2 cache is 10 to 1. So 10% is where the compiler lives. That's where the compiler lives. The 90% case that our work is in memory access, that's on us. That's on the programmer to optimize that. The compiler cannot reason about that. It has no idea about that. So now I rewrote the code, doing a data-oriented model. So what changed? Well, the first thing I did was I got rid of that stupid monolithic structure. There's no entity anymore, okay? And I've separated it into two different things. I've separated it into an entity in and an entity out. You may notice that I removed some of the fields, like you don't see the name, you don't see the model pointer, whatever. And the reason I removed it is because for this particular data transformation, update magnitude, that data doesn't matter. I don't care about that. So I got rid of it. So now what does this function do? This function, instead of updating one magnitude, will loop through a bunch of entity ins and update all their magnitudes. So let's see what this happens to this. So since we separated into read and write data structures, we're encapsulating only the data that we care about, right? We now update magnitudes across a large array of entities. And this scales across the time axis, right? We know that the most common case is that we'll have multiple entities, right? It's not one entity. There's no one player in your game, right? What kind of game is that, right? There's going to be multiple entities. So this function now scales across multiple entities. That's the most common case, right? It's only going to be the crazy 1% chance that we'll ever have one entity, and oh no, we're going to have to go through the for loop only once. Big deal, right? We didn't idealize the problem. So let's take a look at some of the cache properties of this. So if we were to access entity in and out in groups of 4, highlighted by green, let's say we had arrays of 4 for each of these. That's about 16 bytes for the entity in, that's 64 bytes. That fits well in the cache line, 64 bytes. And then we have 4 times 4, 16 bytes for 4 entity outs. That's only 16 bytes. Ooh, I don't like that. That's 48 bytes in the cache line that's wasted. That doesn't sound good. How do I fix this problem? I know. Just up the count. So now I'm going to consider 32. Okay, if I do 32, what does that result in for entity in? So that means I'm accessing 32 entity ins at a time. 32 is going to equal 64 times 8 bytes, which is going to equal 512 bytes, right? That's pretty good. That fills up 8 different cache lines, right? 64 cache lines times 8, so that's 8 cache lines. And now entity out will actually pack out 2 full cache lines. That's 64 times 2. That's 2 cache lines that are used. Wonderful. That's what I want. I don't want to waste the cache line, right? I want to use it. So now that I have 32, let's take a look at what happens. Okay? So we have 32 divided by 8, which is like 4 loops per cache line read. Okay? And then, so 32 accesses divided by 8 cache lines, let's say. Well, this should have actually been 10. I'm sorry, my math screwed up here. Should have been 32 divided by 10. So then square root plus the math that we're doing, so that's like the other stuff, that's 40 cycles times 4. That's 160 cycles per cache line read. That's pretty good. And because we're using arrays, we're going to store these as arrays, the prefetcher in our CPU is going to give us a massive performance bonus in linearized access. We actually allowed the compiler to do some real optimization here by creating a linearized access and using the cache lines correctly. We're actually helping the compiler by doing this. So we have some big reasons to celebrate with this reordering of the data and rethinking the function. We can now reason about the cost of changing this function. If I change the count of entity in that little exercise I showed you, you can reason about the cost of the function now. What does it mean to change the count? Number 2, the data format of our structures is far more maintainable. We now have much less data that we're considering. We're only considering the data that we care about. And if we wanted to do operations on the name and model stuff that we had before, we can create structures for those too. So the data formats are much more maintainable. I know exactly what's going on. We have an in and we have an out, right? We have the thing that's coming into the CPO and we have the thing that we care coming out of it, right? In this case, it's the velocity and a magnitude and then a new magnitude. And 3, we haven't tried to idealize the problem, okay? We've solved it directly, okay? There's no crazy abstraction like make this monolithic entity class that has no purpose other than to confuse you. I mean, how often has it been you've gone a piece of code and you're like, what the hell is going on? I don't even know what's happening. I'm looking at this function and I have no idea what it does. That's object-oriented programming. That's what you've been taught. So, the finality. We've got to replace dogma with reason, right? We've got to change our mental model here, right? So let's start with the good news. The good news is that most of these problems with data access are pretty easy to see. It's pretty easy to look at an object and be like, oh, what are the data transformations that I care about? What is the most common operation on this piece of data? What is the most common operation? How often does it happen? What else is brought in with that data transformation? It's easy to see. 2, solving the 90% data access problem unlocks the compiler to solve the other 10%. It allows the compiler to actually reason about the other optimizations that it's capable of doing to supersede, but not supersede, but to complement our own. Organizing the data makes maintenance, debugging, and concurrency so much easier. If we go back to that code, we had an array of entity ins and an array of entity outs, right? How easy would it be to put 4 of those entity ins, let's say hypothetically, on its own thread, and another 4 on its other thread, and just do them in parallel? It's trivial, right? It's so easy. How easy would it be to have like an array of monolithic entities and make sure that threads are sharing the same state and they're trying to do trying to lock on certain. It's just a joke, right? It doesn't even make sense. Nobody's going to want to do that. So here's the bad news. The bad news is that good programming is hard. That's the bad news. Good programming is hard. And bad programming is really easy. I've seen a lot of bad code in my life. Really bad. And it's really easy to make bad code. But if we reason about the code, if we reason about the data, you can make it better, right? You don't have to be this guy staring at your computer. Okay? So what are the 3 truths? I told you what the 3 lies are. What are the 3 truths? The 3 truths is that hardware is the platform. The second truth is that you need to design around the data, not around the code. And not around an idealized world of what you think the code does. You design around the data. And the third truth is that your responsibility as a software engineer is to transform data in the fastest way possible. That's it. That's your job. So solve that first. Forget about the objects, forget about all this crazy abstraction, forget about trying to make things nice and future-proof, forget about trying to make sure your code will last for 50 years. It doesn't make any sense. You can't. Yes, Camila.
So what if you're working on like old code that's already messed up in object-oriented?
So that is often the most often case we're put into as engineers, right? You're not allowed to start from scratch. You have to come to a code base that's already there, right? How do you solve that problem? That's a hard problem to solve. But the suggestion that I would give if you have that is the first thing you want to identify when you go into that code base is you either want to pick a section or look at the general architecture and ask yourself this question. What is the most common data transformation that happens? What is the most common operation? And on what structures does that happen? And now, you look at that structure and you say to yourself, okay, what other types of data or what other transformations are happening within that don't make sense, that actually impede the performance? What data in that most common case do I not care about? And you just completely refactor that step by step. It's hard. That is a hard problem. But the idea is that you always want to look at the most common case and optimize for that. That is what you optimize for, not the most general case. Generalized case, that won't help you. All that does is makes it so that some guy later down doesn't know what the hell you're doing and you thought you made it easy, but he doesn't understand what you wrote, right? He has no idea what you wrote or what you were thinking, right? It doesn't do anything. It's just something you created for yourself. You made it up for yourself. That's often what is the case. So you want to replace that with reason. That's the best thing we can replace it with. Does that make sense?
Yeah. Thank you.
So, and finally, don't ignore the real problem, guys. Free yourself from dogma, okay? I'm serious. Just don't ignore the real problem. The real problem is that we polluted our code bases with all these crazy abstractions. You don't need them. You don't need them. You can free yourself from that. So do it. Thank you. Any questions?
One.